In this lecture, we will be first discussing the force on a current carrying conductor in a uniform magnetic field. For this, let us start with a magnetic field given by B. So now we are considering a conductor, a current carrying conductor of length L and area of cross section A. Let us suppose that this conductor, the length of this conductor is making an angle of theta with the given magnetic field. Now we all know that the current carrying conductor, it has a pool of electrons, and these electrons inside the conductor, they move with the velocity called drift velocity, which we have already studied in the previous chapter, current electricity. Now the direction of current is always in the opposite to the direction of flow of electrons. So if the direction of electron velocity, which is drift velocity, is in a certain direction, the direction of current will be in opposite to that. We are trying to find out the force on the conductor having current kept in a uniform magnetic field. So now the magnetic force experienced by an electron, it is given by, not electron, let us suppose first a charged particle. It was Q into V cross B, where Q is the charge on the particle, V is the velocity with which the particle is moving, and B is the magnetic field. So here we are considering the electron, force on an electron. So force on one electron will be F is equals to minus E Vd cross B. Minus E is for because the charge on one electron is negative of E, and these electrons inside conductor move with the velocity called drift velocity. What is the trick here? The trick is that first we are finding out force on one electron, then we will find out how many electrons are there in this conductor. After that, we multiply this force with the total number of electrons in this conductor. Proceeding, if small n is the number density of electrons, what do you mean by number density? Number density means the total number of electrons per unit volume. That means the number of electrons in 1 unit of volume. This is small n. If A is the cross sectional area and L is the length of this conductor, then total number of electrons in this conductor will be volume into number density. So first we will find out the volume of this conductor. What will be the volume? If area of cross section is A and length is L, then volume will be equals to A into L. If volume is this much, then what will be total number of electrons? This volume multiplied by the number density. So this is the total number of electrons in this given wire. Now force experienced by the electrons in this given wire. Total force will be equals to the force experienced by one electron multiplied by the total number of electrons in this given wire. So putting the value of F dash from here and the value of capital N from here, we get an equation. This total force experienced by electrons in this conductor comes out to be minus NEA Vd L cross B. In third chapter, if you remember, you have already studied current I is equals to NEA Vd. So here if you see, it is written as NEA Vd. We can write this as I. So now it comes out to be I into L cross B. So the final final expression for the force acting on this current carrying conductor is F is equals to I into L cross B, or ILB sin theta. Next, how can we find the direction of force on that current carrying conductor? We have already learned the expression. So we can find the direction of force by using Fleming's left hand rule. The index finger of our hand will represent magnetic field, represent the direction of magnetic field. The thumb will point us in the direction of force, and the middle finger will point in the direction of electric current. So if you stretch your left hand so that your first finger, second finger and your thumb are perpendicular to each other, then your thumb will point in the direction of force.